Okay, so this section then is about cosmology, and cosmology is study of the universe as opposed to astronomy, which is studying the stars. Astro is to do with stars, so cosmology is to do with the cosmos, in other words the universe. And so this bit of the course is about how the universe began, how it evolved, how we know that, information that we can use to predict things, and stuff about what, you know, what's going to happen to the universe, and you know what happened at the beginning and that sort of thing. So so this is cosmology, and I want to let's just share with you the bit of the so this is sorry, this is the 6-mark question section. Cosmology is this bit, but there's no information in there yet. What I want to do is to show you the option topic teacher's notes for this section on cosmology. So let me just scroll through to the cosmology bit. HR diagrams. Okay. Neutron stars, black holes, cosmology. There we go. So this is the section that we're going to do now. So so this is about how we know what we know about the beginning of the universe, what we know about how the galaxies and stuff are moving with respect to one another, kind of like mega distant stuff. Okay, so so we're going to start then with the Doppler effect. Now, it says here, can you see, most people are familiar with the change in pitch that occurs as an ambulance moves past when the siren is going. So let me just pull up a Doppler shift example. Okay, so Doppler shift. Okay, and this then, I want amazing Doppler effect. That's short. Could you hear the change in pitch? So when it was coming towards you, it's higher pitched. And it goes lower pitched as it's going away. Right, so what that is that the source of the waves is moving relative to the observer. And when the source of the waves is coming towards you, in this case it's a train and the waves happen to be sound, but it works with light as well. When the source of the waves is coming towards you, then the waves get squashed and the wavelength is shorter, and consequently the pitch, the frequency goes up because each of the maxima arrives sooner, right? So so you end up with a higher pitch in terms of sound, or a higher frequency. Okay, so this is a higher frequency wave because the source is coming towards you. When the source is moving away from you, you end up with a lower frequency. Okay, so and I want to let's pull up Walter Fent. Right, so Walter Fent. Whoops. If you've not come across Walter Fent and his animations, can I suggest that you do? Can you see in this top URL bar? There it is, Walter Fent, and he's German, so it's a .de. But you can find it just by putting in his name, which is here. You do need to use sunglasses to look at his web page. But these are simulations of things that are the physics is right. So what I was going to do is just click on the Doppler effect one. And let's enlarge this. So you are the little guy that stood between the two houses. And as the ambulance is coming towards you, you can see that the waves arrive at a higher frequency. They're arriving more frequently. Okay, so that's a higher pitch or a higher frequency. And as the ambulance now is moving away, the ambulance is still producing waves at the same rate, but because the source is moving, what you hear in the case of an ambulance is a lower frequency because the waves have been stretched in effect. So you've got this is the Doppler effect. Now, when we are talking about the Doppler effect in cosmology, we're talking about the Doppler effect on the sources of waves in space, which of course are stars. Okay, it might be a star, it might be a whole galaxy of stars. So that's the Doppler effect that we're talking about when we're talking about space. Let me go back to here. So this is the Doppler effect. So this is the change in frequency of a source of waves if the source is moving relative to the observer. Okay, and this is what we call, well, this is redshift. Okay, so we've got Z is redshift. I don't know why it's Z, but that's the symbol for it, and it is approximately equal to the change in frequency divided by the frequency, which is V over C, or it's approximately equal to the change in wavelength divided by the wavelength. And that technically is negative because red means it's getting longer. But if you call it red, then you didn't ought to also use the negative. So just be a little bit careful. I mean, it says here, notice the negative sign. This reminds us that the wavelength decreases if the source is approaching. But so what you need to do is talk about redshift, and then it's moving away. If you call it red, you don't need to use the negative. Okay, so and in space science, in cosmology, we only ever really talk about redshift because pretty much everything in the universe is moving away from us. That's not quite true. So for example, Andromeda, which is one of the next nearest galaxies to us, that is moving towards us, and eventually in about 200 million years it's going to collide. But yeah, it's yeah, I mean, you know, you don't need to duck yet. Yeah, it's going to be a while, but virtually everything else is moving away from us, and the further away from us it is, the faster it's moving, and that's Hubble's law, and we'll come to that in a minute. Okay, so this is the Doppler effect. Right, now I want you to notice that this is a fraction, which means that imagine that you've got a line spectrum that looks something like this, right? And this is increasing wavelength. Okay, so lambda's getting bigger to the right. Okay, just imagine that's the way that the spectrum is. Okay, right, now, if you look at a Doppler shift of that element, right? So it might be an absorption spectrum, it might be an emission spectrum, but everything is shifted to the longer wavelength. That's a red shift, so everything is stretched, right? The bigger wavelengths, because the fraction is the same, they get stretched more. So all of them move to the right, but the further right they are, the more right, oops, that's not right, the more right they've moved. Okay, so we get this one and this one, and then this one, and then this one, something like that. Can you see? It looks, it's shifted, but it's also stretched, both, because it's a ratio that's going on. Okay, so this then is a stretched version of the one above it. Okay, so this is red shifted. So in order to figure out how fast the source is going, you need to work out the difference. So there is my lambda, delta lambda rather, okay? And you have to divide it by, and this one is the wavelength in the lab. In other words, where you're not moving relative to the source. Okay, that's the wavelength in the lab, and it's that fraction that gives you, this is the speed, in this case of recession, divided by the speed of light. Okay, so that's the redshift thing. Okay, it's a fraction, so the bigger the wavelength, the bigger the shift, right? Okay, right, so that's worth mentioning. Right now, this Doppler effect, we can deal with stars and galaxies, but you can actually do it with binary stars. Okay, so I hear you say, what's a binary? Okay, so binary stars are where two stars go round each other. And people seem to think that binary stars are rare, but they're not. They're really common. In fact, most stars are binary stars. And it's got to do with the fact that if you've got a big dust cloud that's collapsing in to form a star, but the dust clouds that form stars are absolutely humongous. I mean, they're light years across, right? So huge, 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 huge things. Obviously, doesn't have to be moving much before you've got a significant angular momentum, and then it spins as it falls in. Right now, if it spins fast enough, then it can't fall in, just like the Earth doesn't fall into the sun because it's going around fast enough that it doesn't fall in. Okay, it keeps missing, basically. That's what we mean by, orbital motion, right? So if a dust cloud is spinning fast enough, it won't collapse. So if you happen to have a really humongous dust cloud and bits of it are spinning in different directions, it's much more likely to collapse. Well, if you've got things spinning in different directions, you end up forming more than one star. But they're gravitationally influence each other, and you end up with both stars orbiting their common center of mass. And it's not limited to two either. I mean, if we look at our local area of the Milky Way, we can find about 20 other stars that have exactly the same optical emission spectrum that the sun does. So almost certainly those 20 odd stars were all formed from the same dust cloud, which was triggered into becoming stars probably by the supernova of the parent of the dust cloud. So we know that the sun and the Earth and all of the planets were formed from a dust cloud which had been a previously exploded star. And the reason we know this is because they're all the elements present. All of them. So so we know that that dust cloud had got, well, quite a lot of iron in it, which is we now have as the core of the Earth, and every element is present in the sun. I mean, we've got really heavy elements in still present on Earth. Uranium has a half-life of about the age of the Earth, so 4,500 million years. So about half of the uranium that was present in the Earth when the Earth formed is still here, and we can find it and we use it in our power stations and stuff. And the uranium can only be made in an unfavorably energetic environment. In other words, you can't make heavy elements except when a star explodes. So you have to have a hugely energetic environment to force that many protons and neutrons together. If you don't have a hugely energetic event, then the end point of the star output is iron. Okay, so you end up getting as far as iron and then no further, which is why there's such a lot of iron in it. Sorry, I'm being offered a coffee. There's such a lot of iron in the universe. Okay, so the end point of stars until they explode, if they don't explode, the end point of stars is iron. Okay, so a star will run out of fuel when it gets to iron because that's the maximum binding energy per nucleon. So pushing more nucleons into an iron nucleus actually uses energy rather than generating energy. So it's not energetically favourable. So we know that the sun was made from a previously exploded star that went through its entire life cycle and exploded, and then formed all these other stars, right? So, but we also know that stars frequently form binaries. Right, I want to demonstrate this to you. Okay, I'm going to share my screen, and then I'm going to do this and pull up Stellarium, which is free, by the way. It's also open source, so if you're interested in that sort of thing. So Stellarium is a simulation of the night sky, and it's a really good one. I mean, it's accurate, and although it's not real. So what I'm going to do, because it's daytime at the moment, you can't see any stars. So I'm going to accelerate time, which you can do with Stellarium. So there we go. There goes the sun. It's going to set in a minute. There it goes. Down it goes. Diddly doodly doodly doo. And we've got twilight, and the sun sets and the stars come out. Look at that. Oh, and look, there's Orion. Isn't that fun? And we can go and have a little look at Betelgeuse. And oh look, it's a pulsating variable. It's actually a double star. A binary. Okay, we only discovered that Betelgeuse was a binary last summer. Apparently it's got a little blue star going around it. And so yeah, Betelgeuse is a binary, and it says so. Can you see up here in this top left hand corner, pulsating variable double star? Can you see? That's the type of star it is. But and of course, look, there's Jupiter. So if you wanted to go out and look at the sky tonight, there is Jupiter in the night sky. And you can see these are the Galilean moons, and there's another one behind, you can't see it, which is Callisto. There are 4 Galilean moons. So yeah, Jupiter, very, very easy to see with the naked eye, looks really, really bright in the sky. Okay, so, but we're not looking at Jupiter. I'm just going to click randomly on stars. And that one's just one star. Can you see? Type star. Okay, I'm going to pick on that one. That's a double star. What about that one? That one's just a star. What about that one? That's a double star. Just a star. Double star. Can you see? Eclipsing binary. Oh, right now, an eclipsing binary is what we're going to talk about now. Okay, so this is a binary star system. So in other words, 2 stars going round each other, but the plane of the rotation happens to be, we're looking at the plane of rotation. So it's like we're looking at the edge on of a saucer. Okay, and so this is an eclipsing binary, this star that I've got my thingy round. Okay, right now, I mean, I was just lucky picking an eclipsing binary, but you can see how many stars are binary stars, loads and loads and loads of them. And if you wanted to have a go with it, Stellarium, just put in Stellarium into your search engine, and then go and download it. It is quite big, but it is really cool. If you're interested in the night sky at all, it's just very, very cool. And you can go and look at stuff. And can you see the Milky Way going across here? Okay, can you see it? Maybe you can't. Anyway, right, okay, I'm going to close that. So this next section is about an eclipsing binary. Okay, binary star systems. So if you've got 2 stars, they're never quite the same. Even if they were, as they go round each other, one of them goes in front of the other and blocks out the light. Remember that stars are black bodies. They absorb the light that falls on them. So apparently the star becomes dimmer. And then it comes out brighter again because you've now got 2 stars. So can you see the brighter star in front gives you a slightly less of a dip, and the dimmer star in front gives you a bigger dip. So you can see that the absolute magnitude it goes through, it's the square wave. This is an eclipsing binary, okay? And what we can do is we can, I mean, it says the time in days. So these stars, they go around each other in a number of days, okay? And so you get this dimming of a star when you've got another star coming in front of it. Right now, when you look at the wavelengths of light from just one star, as the star comes towards us, the wavelength is reduced. And as the star goes away from us, the wavelength is increased. So here, the wavelength is big, so it's moving away. And here, the wavelength is small, so it's moving towards us. Now you can see that it's not moving, changing the wavelength very much. These are all 656 point something, right? So it's not changing it much, but we could work out the velocity because the change in wavelength divided by the wavelength is equal to v over c. Okay, so we could work out what the velocity is, okay? So the maximum velocity is going to be given by the maximum change, okay? So let's do it. So our change is 656.34 minus, oh, it's 34, it's 35, isn't it, actually? Let's do it properly, 35-ish. 35 minus 656.21 is close enough, right? Divided by, and the actual wavelength when it's not moving towards or away is 656.28. Okay, let's work out that fraction to start with. So 656.35 minus 656.21 divided by 656.28. Now obviously they're all in nanometers, but it doesn't matter because it's nanometers on the top and nanometers on the bottom, so they cancel because it's a ratio. Okay, so we end up with that it's equal to 2.13 times 10 to the minus 4. So if we then multiply that by c, we get our velocity. So v is equal to delta lambda over lambda times c, which is 2.13 times 10 to the minus 4 times 3 times 10 to the 8. I haven't got enough room. Equals, right, so times 3 times 10 to the 8 equals, and we end up with a speed, a maximum speed, either towards or away from us, doesn't really matter, is 64000, and this is meters per second. So the actual speed is 64. Let's do it in kilometers per second. Okay, so 64 kilometers per second, either coming towards us or away from us when they go around each other. Isn't that cool? So we know, can you see how easy it is to work out a speed from a Doppler shift? Ha ha, ha ha. Okay, so we know that the orbital period is 8 days because we've got, can you see, you can work out the period, it's from 2 to 10. So t is 8 days. Okay, so we can now work out, well, we can work out how far apart they are, can't we? Okay, I want to get rid of, sorry, let me clear away all of this because it's just going to get in the way of you reading the next bit when I move it up. Da, 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 da. So let's move this up. So they've gone, we did maximum from one to the other. That was what we did. I did the total change, and of course it's either bigger or it's smaller, not both. So my speed, oh dear, that's bad. So sorry. So really this one should have been that. This one should have been that. So let's make it that. Oh, so let's make it that. So that's 2.8. Da, da, da. So we end up with half of this number. So this is 1.07 instead of 2.13. And then we multiply that by 3 times 10 to the 8. Let's put it in 1.07, get it right, 1.07. And then instead of 64 kilometers a second, it is only 32. So equals 3.213 meters per second. Okay, so it's 32 because it's to the middle. I shouldn't have done it from peak to a trough. I should have done it from peak to the middle, shouldn't I? Ugh, not thinking. Shows you how easy it is to get these things wrong. Okay, so so there we go. So we've got our speed right now. With the orbital speed and the time period, the diameter of the orbit can be calculated using the circular motion equation. So you assume that you're going in a circle, and you can say that the circumference is equal to the orbital speed times the period. It's just speed is distance over time. Let's do it. Speed is distance over time. Okay, so our distance is the circumference of the circle, so 2 pi r or pi d, and the time is the period. Okay, so if we want d, can you see it's going to be v times t over pi. That will give us our diameter. Okay, so where's their pi? Speed times 8. Oh, that's the circumference, and then they've divided it. There's the pi. I'm going to do it all in one go. I don't want to do it in multiple steps. So I'm going to do it all in one go. So d then is equal to the speed, which is 32.123, times the period, which is 8, but that's in days and we need it in seconds. So it's 8 times 24 hours in a day times 3,600 seconds in an hour, divided by pi, and that gives us the diameter of the orbit. So let's do this. 32123 times 8 times 24 times 3,600 divided by shift pi equals a really big number. So we press our engineering button and we get 7 times 10 to the 9 meters. So that is 7 times 10 to the 6 kilometers. So it's 7 million kilometers between these two stars. So now bear in mind that the sun is 150 million kilometers. No. No, that's right, isn't it? 150 million kilometers from Earth. That's right. So yeah, they're only 7 million kilometers apart, which sounds like a lot, but it's actually not that far. Okay, so there you go. That is eclipsing binary stars. Okay, right, let's move on. Okay, I want to talk about Hubble's law then. So we've talked about the Doppler effect, and we've talked about the fact that you can use it to work out the speed of something. And Edwin Hubble, he figured that you could then apply the Doppler effect, this shift, to work out the speed of recession of loads of stuff, right? And what he discovered was that if you knew how far away things were, you could then work out the relationship between the distance along the bottom, speed up the side, and you should get a straight line through the origin, right? And if you do this, you will get the gradient of the line, and basically its speed is distance over time. Okay, right, let me show you again. Right, what am I going to do? I'm going to do this, right? So I have got up, right, these. Okay, so what Hubble did, let's minimize that one for a minute. Yeah, so what Hubble did is he said, right, well, if we've got a graph of velocity against distance, right, speed is distance over time, can you see that the gradient should be 1 over time? right? So if this is velocity against distance of things in the universe, then what's the time? Okay, so basically this was suggesting that these objects all used to be really close together and they're all moving away, and they've been moving away from each other for the same length of time. And the length of time then is the gradient of the graph. Okay, you look there, compare it to y is mx. Okay, so the gradient isn't the length of time, it's 1 over the length of time. And he called this, well, he didn't, I think somebody else did it, but it's called the Hubble constant. So basically you end up with a straight line through the origin, and the gradient is the Hubble constant. Okay, and the Hubble constant, if you do 1 over the Hubble constant, you get the age of the universe. Because all these objects have all been moving away from each other for the same length of time. Okay, right, now, the difficulty was, it was easy to measure the velocity. You can just look at the redshift, and it's dead easy to measure the redshift. Really, I mean, really easy to measure the redshift. So it's really easy to figure out how fast these objects are moving away from us. What's difficult is knowing how far away they are. Okay, so, and this particular graph is a Hubble diagram for Cepheid variables. So you remember when I was talking about how stars are formed, and that a main sequence star has got gravity pulling in and radiation pressure pushing out, and where those two are exactly balanced, you end up with a stable star. And that if you don't get them balanced, then the star can kind of breathe, because it gets a bit too big and it cools down a bit too much, and then it collapses in, and then it gets hot, and then it gets too hot, and then it expands again. And this period depends on how absolutely big the star is, how much mass it's got. Which and if you know the period, and you can see the brightness going up and down, if you know the period, and you know how bright it appears to be, apparent magnitude, then you can work out the absolute magnitude, absolutely how big it is. So this sort of star that sort of breathes, it's called a Cepheid variable, and you can see that this diagram is labeled Hubble diagram for Cepheids. Okay, so this is a Cepheid variable. Right, now you can know how far Cepheid variables are away from you, because from the period you know how absolute big it is, and from how bright it appears to be, you can then work out the distance. Okay, so useful. The trouble is that it only takes you to sort of 20 megaparsecs. Okay, which sounds like a lot, but it's not in the great scheme of things. 20 megaparsecs is not that far. Okay, so we need something that is brighter than a single star in order for us to be able to expand our Hubble diagram for the whole universe. Let's see if we can do it. So we need this Cepheid variable thing, something where you know how absolutely bright it is, so you can work out from how bright it appears to be, how far away it is. That idea is called, it's a standard candle. Okay, so the Cepheid variable is a standard candle. In other words, we know how bright it is. Okay, so from how bright it appears to be, we can work out the distance. So we need some other standard candles. And the other standard candle, which was the one that I minimized earlier. So I think I might, can I just step across to it? Oh, no, not that way. Can I go the other way? Yes, I can. Right, so the other standard candle then that we end up using is something called a type 1a supernova. Right, now a supernova is where a star explodes, but a type 1a supernova is a very special supernova. So if you've got one of these binary stars, one of the stars tends to be bigger than the other just by accident, and goes through its whole life cycle faster than the other one. And what happens is then that it explodes in a supernova, right? Well, the first time it could be any size supernova, but after it's exploded once, and imagine that you've got a neutron star, now you've got a neutron star and a regular star going around each other. Okay, so again, it's still a binary, but our neutron star, it's really dense. It's going to be pulling material from the other star, and so stuff from the star that's not finished going through its life cycle will spiral into the neutron star, and the neutron star will collect extra mass from its companion, and eventually, when it gets to a known size, it'll explode again. And that is a type 1a supernova. And we can tell that it's a type 1a supernova from what's called the light curve. So you end up with the light going up quite sharply, and then it dips off, and then it sort of levels out and eventually drips down. And from that shape, you know that it's a type 1a supernova. And type 1a supernova are always the same brightness. It's a standard candle. Yay! So, from how bright it appears to be, you can tell how far away it is. And a supernova, unlike a Cepheid variable, is incredibly bright. Supernovae outshine their galaxies, unbelievably energetic events. So you can see supernovae in other galaxies, and really very distant galaxies. And so now, even though supernovae are very, very bright, you can see that we still only get to sort of 600-700 megaparsecs this way, and the error bars on the distance, not on the speed, but on the distance, get to be really very big. Okay, so but having said that, can you see the fit of the line? And now we've got a much more convincing straight line. And remember that the Hubble constant is the gradient, and 1 over the Hubble constant is the age of the universe. Yay! So this is Hubble's law. So Hubble's law is this one. Okay, so V is equal to HD. Okay, and sometimes it's called H naught, but sometimes it's just H. It's the Hubble constant. Now, the Hubble constant's got horrible units. Obviously, it's the gradient, so it's kilometers per second per megaparsec. So, the unit the Hubble constant, it's around about 70 odd, 73 kilometers per second per megaparsec. Okay, and if you convert that into meters and seconds, and the megaparsecs into meters, the meters cancel, and you end up with seconds to -1, and you end up with that if you do 1 over that, you get the age of the universe, and it's around about 10 to the 17 seconds is the age of the universe, ish. Okay, which is about 13.5 billion years. Okay, so it doesn't seem like lots when it's 10 to the 17 seconds, does it? But yeah, it's a long time. Okay, so this is Hubble's law, and it gives us the age of the universe, which of course is kind of cool. Okay, how long have I got? How am I doing? Okay, so I've got about another 20. Oh, when am I stopping this? I can't remember. 1:45. I was going to stop at 2:45, and then from 3 o'clock to 4 o'clock. Yeah, so 2:45. So I've got 20 odd minutes. Right. Okay. So the Hubble is the Hubble law is this one, and yeah, you need to be able to manipulate these units. So let's have a go at that. On your data sheet, incidentally, let me clear the drawings a minute, and then can I find the data sheet? This is the question. Let's close that one, and close that one, and let's maximize that one. Where is my data sheet? Data sheet. So if you go and look at the data sheet, down to the astrophysics, where it is. Oh, there it is, astrophysics. Right, the Hubble constant, the best guess, as it were, of the Hubble constant has changed since the course started. So on your data sheet, Hubble's constant is 65, not 73, but 65 kilometers per second per megaparsec. So what we're going to do now is we are going to work out the age of the universe. So this is h, and we're going to first of all convert it into seconds to the minus 1. So h then is 65. Now we're going to put it in meters, so it's in kilometers at the moment, so we need to multiply it by 10 to the 3. Okay, now it's in kilometers per second. Okay, and it's per megaparsec. So what we've got to do is we've got to divide it by the number of meters in a megaparsec, which is, right, that's in 1 parsec. So it's 3.08 times 10 to the 16. That's 1 parsec, but it's times 10 to the 6 because it's in megaparsecs. Okay, so let's do this. So it is 65 times 10 to the 3 divided by 3.08 times 10 to the 16, and then also dividing it by 1 times 10 to the 6. Okay, and we end up with 2.11 times 10 to the minus 18 per second, seconds to the minus 1. So the age of the universe is 1 over the Hubble constant. So it's 1 over 2.11 times 10 to the minus 18, which works out to be 4.7 times 10 to the 17 seconds. Okay, right, now if you want the age of the universe in years, okay, so we need to divide our 4.7 times 10 to the 17. We divide it by 60, that's in minutes, by 60 again, that's in hours, by 24, that's in days, by 365, don't worry about the quarter, that's now in years. So let's do that first. Divided by 4 times 3,600 times 365. Okay, and we end up with 1.5 times 10 to the 10. This is years. Okay, right, now remember that 10 to the 9 is a billion years, isn't it? So it's about 15 billion years. Now, nowadays, I mean, we think that the age of the universe is about 13.8 billion years. So it's a little bit of an overestimate because our estimate of Hubble's constant has gone up a bit. Okay, so the age of the universe is a little bit less. Okay. Oh, I've got a chat. What does it say? Okay, so it's like an indicator which we can determine other objects' distance because we know the distance of the type 1a supernova. Well, you can, right, you can tell how far away the supernova is, and if the supernova is in a galaxy, then you know how far away the galaxy is. Yes, so you can see supernovae in other galaxies. So if I clear this, I mean, that's a really good question. If I clear this and let's right, I think I'm going to have to open another window, and then let's close that. Right, so a supernova in another galaxy. Okay, and we want images, please. So you can see supernova in other galaxies. what we want is something where I can compare it to, so here. Okay, can you see the supernova? That's one star exploding. And if you're interested in this sort of thing, there is something called the supernova portal. Just do a search for supernova portal and you get the supernovae reported to you if you opt in their notifications. So there, that's I think that might be the Phantom O's pinwheel, and you can see the supernova. It's brighter than the center of the galaxy. It's unreal how bright these things are. So there is a supernova. I think we've got another one, a second one. Can you see on the other side of the same galaxy? Okay. It's so interesting, isn't it? So, and you know it's a supernova if it wasn't there, and then suddenly it is. Anyway, these are supernova remnants. I don't know what that is. That's somebody's artist's impression of something. Anyway, okay, so yeah, you do need to be careful with astro images as to which ones are real and which ones are not. Okay, does that answer your question? I hope that satisfies you, Theo. Yay, okay, cool. Right, so let's move on. What I want to do now is I want to talk about the Big Bang and the evolution of the universe. So we have now then, from Hubble's law and the fact that everything seems to be moving away from us, come to the conclusion that the universe is expanding. And in fact, we've got a bit of a problem because we know the universe is accelerating away because we've measured it. And that's a problem because we've got no mechanism for that. And we end up having to invent something called dark energy, which we can use to explain, not really, but explain why the universe is accelerating away. So yeah, dark energy, nobody really knows what that is. It's stuff that pushes. And gravity only pulls, right? So gravity can't explain the acceleration. If it was moving fast enough when it exploded, then it will keep on going forever, but it will slow down and slow down and slow down and slow down as it does it. But we know that's not what's happening. So we've got a problem. There's something we know we don't know. And so we've invented this thing called dark energy, which explains the acceleration. Except it doesn't really explain anything. We've just called something called dark energy. Nobody's ever found any. Yeah, so we've got problems. We know that we don't know stuff about the universe, which is kind of exciting. I mean, it's quite fun knowing that you don't know stuff. But anyway, so what we do know is that the universe used to be, in the far distant past, all in one place, and then Hubble's law expanded from there. So we the term Big Bang was coined, and it gives you this impression that it's an explosion. It's not really an explosion. In one way, and yet it is in another. It's like a beginning of space and time. It's the beginning of everything. People can ask questions like, well, what was before the Big Bang? Well, it's a meaningless question because time is decided by the things changing. And if you can't know what was before the Big Bang, so it doesn't have a meaning. It's like, what's the difference between a duck? Yeah, it doesn't have a meaning. You can say the words, kind of a question, but it sort of doesn't have a meaning. So we've got then this idea of the Big Bang being the beginning of space and time, the beginning of energy and matter. That is what we really mean by the Big Bang. And if we work our way back, we can make predictions about, well, predictions is not really predictions, is it? About what the beginning universe was like from what it's like now. There are some things that you need to do in order to make predictions like that. So there's something called the cosmological principle, which is that the universe is pretty much the same. It looks the same no matter which direction we look in. It's not quite true because the sun is in the Milky Way, and the Milky Way is right across the sky. And so when we look towards the Milky Way, that bit of the universe looks different because it's filled with stars. But if we look in any other direction, pretty much it looks the same. And that's the cosmological principle. The cosmological principle says that the universe is homologous. In other words, it's the same, everywhere you look. Everywhere is exactly the same. Now, obviously, on a smaller scale, like galactic scale, that's small, right? On a smaller scale, you've got lumps and bumps. So you've got a galaxy here and a galaxy here and not much between, a galaxy here and there. Those ones happen to be linked. And then there's one over there that's not linked. And yeah, so on a smaller scale, it's not uniform, but on the not the galactic scale, the universal scale, if you like, the cosmological scale, it's the same no matter which way you look. And in fact, we can confirm this because we discovered, two guys, Penzias and Wilson, they discovered something called the cosmic microwave background radiation. So they were trying to do radio astronomy, and they wanted to get the clearest radio pictures they could of the sky, and so they wanted to eliminate all of the sources of noise, so stuff that's not from the sky, in their equipment. Okay, and that's actually quite difficult because we are a very noisy species. We emit lots of radio waves. I mean, these things don't help. They emit radio waves, they emit light, they emit ultraviolet, they emit maybe not ultraviolet, but infrared and microwaves and radio waves and and we deliberately transmit radio waves to each other and UHF and VHF and all the rest of it, loads and loads and loads, and of course so they wanted to eliminate all of these sources of noise, and so they were really, really careful, and they shielded their electronics, and they shielded their the signals that came from it looked a bit like a trumpet, their aerials that they were pointing at space, right? And yet when they looked at the images, they got like a kind of crackle on them. I mean, we call it white noise. If you detune a TV, an old-fashioned TV, you'd get like sparkles of white over, and it's just noise. It's like it's a low level, just sort of hum that's going on. And they thought originally that it was, sort of background from people's transmissions, radio transmissions, and they thought that it might be from, people's electrical equipment. And they did this in the middle of nowhere, up on top of a mountain, so that they were nowhere near any sort of domestic or commercial sources of radio waves, and they couldn't get rid of it. They thought at one point that it might be radio emissions from pigeon guano, because the pigeons like to perch on their aerial, and they sent the pigeons away, and the pigeons came back, because pigeons home, don't they? And they ended up shooting the pigeons, but you had to clean off all the guano. No, it wasn't. They couldn't get rid of this background noise. And they thought originally that it was a problem, and they couldn't get rid of it. How are we going to get rid of this? What are we going to do? And eventually, when they couldn't get rid of it, no matter how hard they tried, they came to the conclusion that it was real. That this background noise that came from every direction, the same level, no matter which way they pointed their telescope, it was a sort of cone thing. In fact, I ought to get a picture of them up. They came to the conclusion that it was real. Okay, so Penzias. Okay, so there it's a sort of cone thing. This is their telescope. Okay, and these are the two guys. These guys. Anyway, so they came to the conclusion that this was real, and eventually they figured that this was the remnants actually of the Big Bang. So this is the cosmic microwave background radiation, and it permeates the universe. and it's, I mean, it's a remnants of the Big Bang, but it's now been very, very redshifted. So redshifted that we're now in the microwave range. And if you compare the microwave range as a peak wavelength on your black body radiation graph, you can find out the temperature of the universe. Not that that really means much, but because there aren't any particles to be at that temperature, you know, space is empty pretty much. But if you were to apply a temperature to space, it's around about 2.7 Kelvin. That's the equivalent of this microwave wavelength that comes across from all of space. Okay, so that's the black body radiation from the Big Bang that's been seriously redshifted. And you can think of it as redshifted because the source is moving away because it's expanding. Or you can think of it as, well, actually space has been stretched, so all the waves are stretched. But it doesn't matter which way you think about it, it's cosmic microwave, it's microwave level. So they are millimeters long, these waves, and it works out about 2.7 Kelvin. That's at 2.7 degrees above absolute zero. So it's cooled down quite a lot, the universe, since it first exploded. And these guys were the first to discover this microwave background. Nowadays, I mean, the Kobe satellite went up, and then since then we've had ever more detailed images of the whole of the universe in terms of cosmic microwave background. Are there multiple universes? I don't know. How could we tell? Maybe. Who knows? I'm sure that somebody brighter than me might be able to figure out a way that we could perhaps tell. But unless something changes in this universe because of another one, I don't know how you'd know. Don't know. Just don't know. Anyway, right, okay. So, good question though. I mean, honestly, sorry, I don't know, but I wish I did, but I don't. Right, so what I'm going to do now is pull up pictures of the cosmic microwave background. Okay, so the Kobe satellite came up with oh well, it was a bit like this, right? It's false color, so the different patches indicate different temperatures, and so but we're talking about really, really minor differences in temperature. And since then, we've had much smaller changes represented. So pretty much it looks uniform. So this is the cosmological principle in visual form, saying it doesn't matter which way you look, it's the same in every direction. So sometimes you get something like this. So what do you think this thing is across the middle of this picture? Can anybody figure out what that must be? Because it's obviously different in that middle stripe, isn't it? Anybody work out what this is across the middle of the picture? Oh, somebody's giving me a thing. Oh, dark energy. No, it's not dark energy. This stripe across the middle of the picture, that's the Milky Way. It's in the way. We can't see that direction because the Milky Way is in the way. We're in it, right? It's a spiral galaxy, but we're seeing it edge on. So that's the edge of it. So if we look up or down, we pretty much look straight out. If we look out the other way, well, we're near to the edge. We're not right at the very edge, but we're near to the edge, so much less stuff in the way. But yeah, so this is the Milky Way. It's getting in the way of the picture. So, but if we look in every other direction, the cosmic microwave background looks the same in every other direction. So, so we can see, so there you go, there's the cosmic microwave as a sphere, and you can see the Milky Way on the equator. Okay, so in every other direction it's pretty much uniform. Okay, so this is then a remnant of the Big Bang. So this is evidence for the Big Bang, which is really, really cool. Right now, I've got another comment. Okay, what are quasars? Okay. Quasars are quasi-stellar objects. So they're objects that sort of look a bit like stars. And in fact, a quasar is another name for an active galactic nucleus, an AGN. Okay, so an active galactic nucleus is a nucleus of a galaxy, which is nearly always a supermassive black hole. And we've got one in the middle of our galaxy. It's called Sagittarius A star, and it is it an object or an event? A quasar is a quasi-stellar object. It's an object. So it's an an active galactic nucleus is one where things are falling in and stuff is happening, and because things are falling in and stuff is happening, light does come out from beyond the event horizon. And so a quasar, if you look at it in radio, or if you look at it in X-ray in particular, you can see jets. So if you look at some galaxies, I know this is such a fascinating subject, but let's do quasar. Okay, so let's see if we can get some pictures. Right, now these are not real. I want a real one. That one looks real. Okay, so there's a galaxy there, and this object is active, and it's producing jets of usually radio, and they extend out light years from the object. So have we got any real ones? That looks real. So it doesn't actually say, does it say whether or not? Yeah, it's a radio source. Okay, so quasar. It's a quasi-stellar object, and it is radio. So these lobes are in the radio. So if I do, let's go back. Where are we? Let's go back and do radio telescope view. Yeah, so obviously this is false color. This object, obviously that object is very, very bright. This over here is a jet from the star in the middle, and that is it's emitting radio. So that's radio, and they can be light years long, these jets. They're enormous. That's the first quasar. There you go, that's a quasar. You can see the jet, and this is an emission from a black hole, and yeah, we think, I mean, you know, it's pretty fairly sure now that quasars are quasi-stellar objects. Okay, I'd like to show you while we're here. Let me put into here instead of Doppler shift. Right, so movement stars around Sagittarius A star. Okay, so so these I didn't mean to do that. What's going on? Whoa, that was weird. Let's look at this one. So this is from the European Space Agency. So this is real motion of the stars in the center of our own galaxy. So you can see that those stars, it's over the course of years, have moved, and they move round something that's really, really heavy that you can't see. It's too dim to see. And that is the black hole in the middle of our own galaxy. Okay, so if we do this one, and this one shows you, oh, let's get rid of the sound. So this one shows you where it is. So that's the band of the Milky Way that we're in. So it looks like a straight line across the sky. And obviously you can't see with visible light through the dust clouds, but you can with infrared see through dust clouds to some extent. And you can see that as we sort of home in on the center of the galaxy, we can start to see the stars that are right in the very middle, and there's a supermassive black hole, and we know that there's there because of the real motion around that that invisible object in the middle. So this is just zooming in. Come on, let's do it. Okay, so here we go. So you can see that there must be something really massive in there that they're going round. Can you see that? Woo! It's in there. Yeah, in that square. Okay, so it's not great images because of all the dust and stuff that's in between us and it. But you can figure out where it must be, right? And look at the dates. So this is over the course of months. Okay, so right, another question. What about that Chandrasekhar limit? Okay, right. So so this has got to do with the life cycle of stars. It's got nothing to do with cosmology, really. Right, when a star like the sun reaches the end of its life, in other words, it's used up all its hydrogen, it will collapse in. Right, no radiation pressure, no heat being generated, so it collapses in. Basically, it bounces off itself and it swells again. But when it collapses in, the middle of it gets hotter, and then you start helium burning and so on. And you end up eventually going through all of the periodic table to iron. And then when you actually run out of fuel, properly run out of fuel, then there's nothing to stop it from continuing to collapse. It doesn't any longer generate heat. So what happens is that under its own gravity, it will collapse and collapse and collapse and collapse and collapse and collapse. Right. Now, there is a limit to how small it will collapse to. Okay. So I want you to imagine that we've got an atom, right? There is the nucleus of my atom, and going around it are some electrons, right? And the electrons might not be in the lowest possible energy level, but if you push lots of electrons in and you push the atoms close together, then what happens is that the electrons, they all fall down into their lowest possible energy level. Okay, and under gravity this happens. Okay, so so you end up with all of the atoms are in their lowest possible energy level, and they can't go any lower. If the thing won't collapse anymore, because all the electrons have all been squished right into the middle of their atoms as far as they can go. They can't go in any further. Well, they can if you push a lot harder. Okay, so and when they're all in their lowest possible energy level, that is called electron degeneracy. In other words, all the electrons are as low down as they can get. They can't go any lower. All the energy levels are full, right? Right down, yeah? That's electron degeneracy, and that is the Chandrasekhar limit, after a man called Chandrasekhar. Okay, and that is what happens with a white dwarf. So the white dwarf, it's not generating heat anymore. It's very hot, but it's not generating heat anymore, and it collapses in under its own gravity to the Chandrasekhar limit, and then it can't go any further because the electrons won't go in to the nucleus. Well, except that they will, and they only go in if gravity is significantly bigger. Okay, so the Chandrasekhar limit says electron degeneracy is the end point for stars less than 1.4 times the size of the sun, something like that. Okay, that's the Chandrasekhar limit. Right, so something between 1.4 and 3 times the mass of the sun, there's enough mass that it can push the electrons further. So what does it do? It pushes the electrons right into the nucleus. And when you push an electron into a nucleus, it will join with a proton and become a neutron. Okay, so and what you make with gravity is a neutron star. Okay, and gravity can only push it so far. It won't go any more dense than each nucleon being neutron being 1 femtometer from the next one, because if you get to half a femtometer, the strong nuclear force, which is really strong, like 10 to the 40 times stronger than gravity, will prevent it from collapsing any further. And the consequence of that is that the star will become a neutron star, and it won't go any further. Except if gravity is even bigger, then that can stop. Okay, so if the strong nuclear force isn't strong enough to prevent, because there's so much mass there, so the gravity becomes huge, and so what happens is that it pushes it past the strong nuclear force repulsion bit, and there's nothing to stop it from collapsing right in. So matter becomes what's called a singularity, and that's what we call a black hole. Does that answer your question about the Chandrasekhar limit? So the Chandrasekhar limit is electron degeneracy limit for a white dwarf. If there's so much mass that it pushes the electrons right into the nucleus, then you get a neutron star. If there's enough mass, so 3 times the mass of the sun or more, I mean, it used to be 7, so I think it's a bit of a movable feast. But anyway, bigger mass again, it can collapse even the neutron star into a black hole. Okay? So, right, now we've overrun. I haven't been able really to talk about what happened at the beginning of the universe very much. From the AQA point of view, you don't need to know the evolution of the universe. From the OCRA point of view, you do need to know what happens in the first few seconds, and when the first atoms were formed, and when the first stars were formed, and when the first galaxies were formed, and you need to know the approximate timeline. It is in your textbook. Go away and look it up. Is what I'm going to say to that.